Okay, part two, voted and average perception. So as we said before, parts 2 and 3 will be devoted to two modifications or two lines of research trying to address perception's problems or two variations of perception. So part 2 will be voted and average perception. That's actually two variations already, but they are on the same theme. Part 3 will be a Myra, which is another kind of a different from a different angle. Um, and uh, why do we need to address the problems of perception? Well, first of all, what's the most important problem of perception? Well, it's the instability of the vanilla perceptron. That is, if you try to use perceptron for your homework 1, for example, which you will do, you'll notice that uh, as training progresses, perceptron accuracy on the depth set or the held out set will be bumpy, will be kind of up and down, um, and it's kind of not very stable. And also the accuracy is not very good. So voted perceptron and average perceptron made it a lot more smoother, as you can see, a lot more stable, and also much better accuracy than vanilla perceptron. Often there is a noticeable gap. Like in homework 1, I believe it's about 4% gap difference between vanilla perceptron and average perceptron. So in fact, voted perceptron, average perceptron, this line of work revives the whole research area of perceptron. As mentioned in week 1, perceptron was dead, has been dead for 30 years, between 69 and 99, because that paper or book effectively killed it, because perceptron is not able to separate the XOR data set, right? But after 30 years, Froehn and Shapira revived perceptron by proposing voted and average perceptron variants. Okay, and as we said before, we try to address the stability problem of vanilla perceptron. And as you noticed in week 2, uh, order of examples actually matters a lot, right? Uh, in fact, later examples often have more votes than earlier examples because it's only after these later examples, perceptron try to kind of fix those later examples. And if the data set is not separable, perceptron will cycle, and it will depend really on when you stop, right? If you stop on, let's say, this example, then chances are that perceptron have fixed it, but causing problems in the other example. Okay, if you remember that exercise problem from week 2, it will cycle, but if you stop somewhere, often that example or the last few examples are taken care of, but the earlier examples were kind of not correct, right? So voted perceptron tries to address that problem by saying that we should let the weight vector after each example vote. Okay, we'll record the weight vector after each example in the dataset D. In other words, we record D weight vectors, one after each example. Remember that it's one after each example, not one after each update, okay? Because you probably only update, like, say, 30% of the training examples. But you do need to record the weight vector after each example, even if there is no update, okay? That's the idea of the voted perceptron. And at testing time, for any new example, you would vote using all these D weight vectors, okay, and take the majority. And if there's a tiebreaker, you can do whatever, but that's unlikely. So that voted perceptron has been shown in this Froehn and Shapiro paper to have a much better generalization power, and in fact they call it large margin perceptron, which means it kind of approximates the max margin behavior in SVM, but it doesn't really, right? So it kind of approximates max margin, so it's kind of large margin. But it's very kind of theoretically beautiful, but practically not very doable because you have to record so many vectors, so many models during training time. Let's say you have 1 million examples. Okay, in today's standards, 1 million examples is not very big either, right? But let's say you have 1 million training examples, and you have to save 1 million weight vectors or 1 million models. And then at testing time, for each example, you have to let each of these 1 million guys, do a prediction and then vote. So it's both memory and speed inefficient. Okay, first of all, memory-wise, you have to save a lot of models. Like, each model is pretty big in high dimensions, so you would have to use a lot of memory. And then it's also very inefficient in terms of speed because you have to do so many predictions, right? So it's a little bit like nearest neighbors, right? At testing time, you have to let each of the training example do its vote, and then take the majority vote. That's kind of inspired by nearest neighbors, but this algorithm does not scale in practice. So the same author in the same paper also provided another approximation. It's an approximation of approximation, right? So voting perceptron can kind of approximate max margin, and average perceptron can approximate voting perceptron. So average perceptron is much easier. Instead of recording all the D vectors of models after each example, you just save the sum or average of all these vectors. So you only have one vector. That vector is the sum or average of all weight vectors. Now at testing time, you just use that average vector to do the job. So instead of having D models do the vote, you only have one vector representing everybody. Okay, I take the average vector, and that represents all these D models. That can be implemented very efficiently. Okay, so this is the original large margin classification using perceptron paper from Fernie Shapira. This is their voted perceptron pseudocode, and in our notation we'll write X superscript 1 and Y superscript 1 to mean the first example, and they use the subscript, but they still have a consistent notation in the sense that X input is a vector, so it's boldface, Y is a scalar, so it's 1 or next to 1, and the list of weighted perceptrons, and C is their relative vote. So in the very, very naive implementation of voted perceptron, you just record D vectors, right? And this implementation is slightly smarter in the sense that in many examples you don't need to update, right? Because you correctly classify that example, so you can just increase the vote of that model, right? So if you correctly classify example I, then you just increase the weight or the vote of the current model. And if you made a mistake, you need to create a new model. So vk plus 1, you create a new model. K is how many distinct models do you create so far? And vk plus 1 is vk, the current model, plus the update. Now, after that, its vote is set to 1, okay? And of course, you have a new model, right? So this is kind of a slightly smarter implementation of voted perceptron. But even that, you have a lot of models. You don't have D models. You probably have like 1/3 of D models, okay? If you make updates on 1/3 of these examples, okay? So it's faster, but not really, right? Still doesn't scale in practice. At prediction time, you just let all these K models do the job, and let's say K is 1/3 of D, okay? And you just take the vote of the ith model and times the vote, the number of votes that you give it to. That means that represents how many training examples have that same model, and this is just to do it slightly faster than recording all the D models, but still it doesn't scale. Okay, but it works pretty well in terms of accuracy, even though it's very, very slow. So if you could run it for like say 2 days, you could afford to wait until voted perceptron finish. Okay, then voted perceptron is really, really nice. Okay, in terms of accuracy, very stable and much better than vanilla perceptron in terms of depth set error rate. Notice that we don't care about training set error rate because you can very easily overfit. Right, we always plot the depth set error rate or held out to kind of simulate the testing time or generation error. Okay, and an average perceptron, which we'll talk next, is a much easier approximation of voted perceptron. It works almost the same as voted perceptron, but much faster. In fact, it's as fast as vanilla perceptron, same speed, but much better, much smoother, and much more accurate. Okay, how does average work? Okay, so average perceptron is an approximation of perceptron by outputting just the average weights, or indeed, you don't need to output the average weights. You can just output the sum weights, the total weights, the sum of all weight vectors after each example. Why average vector is the same as sum vector? Because the sum vector is just average vector times how many examples have you seen, right? So it's just a scalar. And by scaling a vector by, say, 2 or 10 or any constant, you have exact same decision rule, exact same decision boundary. So just scaling up the weight vector by a constant doesn't change the prediction at all. Okay, so that's why instead of outputting average, we just output the sum. Okay, they're exactly the same. If you divide it by a constant, that's exactly the same. So the only difference between this average perceptron and vanilla perceptron is that we have to record this running sum of vectors, right? If you remember, in vanilla perceptron, we have to record each model, but here we just add it up to the running sum. So using one vector to represent all, okay? And geometrically, it looks like this. So you record the sum of all these reddish area. So if it's voted perceptron, then you have to record W1, W2, W3, W4. But in average perceptron, you just record the sum of this area, this reddish, kind of reddish shadowed area, right? And you output that model. And that model is shown to behave much better than vanilla perceptron. And you will verify that in homework 1. Okay, so this is the naive implementation of average perceptron, right? Just like in voted perceptron, there's a very, very naive implementation. There's a slightly smarter or slightly faster implementation. In average perceptron, there's also a naive implementation like this, and a much better, much faster implementation, a much more efficient implementation of averaging. Due to Hal Demey, he's also the author of our textbook, AML, right? Who have been reading his textbook all along. So he invented a very clever trick in his thesis, and it's kind of not well known. So it's one of the hidden kind of secrets in machine learning. So yeah, naive implementation on the previous slide by recording a running sum does not scale for very high dimensions. It kind of works for low dimensions like homework 1. In homework 1, if you don't understand this algorithm, you can just use the one on the previous slide. It doesn't cause you too much trouble, right? If you do the slightly faster, the smarter implementation here, you will notice it runs slightly faster, but not too significant. But things will be very different for homework 3 when you work on much higher dimensions, right? Homework 1, you have about 230 dimensions. So in machine learning, 230 dimensions is very, very, very low dimensional space. Well, you might think 230 dimensions is already a lot, right? No. Machine learning is always on very high dimensions, okay? So in homework 3, you have, I don't know how many dimensions, maybe a million dimensions. And then the previous slide, the method on previous slide just doesn't scale. You have to wait for maybe 10 hours for it to finish. But the one on this slide really works as fast as vanilla perceptron. Exact same speed, same complexity. The reason why the version on the previous slide, just by recording the running sum, does not work, does not scale, is because WT could be very, very high dimensional. WT is the weight vector after tth example. Let's say WT is 1 million dimension, okay? But each update, however, is still very sparse, okay? And that you'll get a feeling after you work on homework 1 and homework 3 that even though the whole weight vector might be very, very high dimension, like 1 million dimension, the update on each particular example is still relatively low dimension, like 100 dimension at most, okay? Because the weight vectors are always sparse, meaning most of them are zeros. Okay, so each update is still low dimension, and you can do this update pretty fast, but you cannot afford to do this kind of update running sum, because this plus is between two 1 million dimensional vectors. But this sum is between a 1 million dimensional vector and a 100 dimensional vector, much, much smaller, right? So what if you can do something very similar to this update, that is 100 dimensional instead of 1 million dimensional? Okay, so this is the idea. Well, geometrically it also makes sense because really you want to kind of get rid of this area, right? So if you kind of use the last weight vector, that's the vanilla perceptron weight vector, times 4 times the number of examples, and that's the square, that's the area of the whole square, minus this bluish area, right? And how do you get rid of this bluish area? Well, you're using the auxiliary weight vector called WA. And WA every time is, instead of plus YX, which is the update vector, or delta W, you times C, you plus C times that update vector. Okay, so C is initially 0, so WA initially doesn't get anything. The second round, WA gets 1 copy of W2, and then 2 copies of W3, and 3 copies of W4. Okay, that's exactly kind of accumulating this bluish area, so that's why we kind of shadow them in bluish shadow, right? So WA, okay, is after each update, not after each example. So as you remember, there are more examples than updates, right? Because you make updates on, let's say, 1/3 of these examples, right? So this is much more efficient than the previous slide for two reasons. One is you don't need to do this auxiliary operation after each example. You only need to do it after each update. And secondly, more importantly, this auxiliary plus is on 100 dimensions instead of 1 million dimensions. Okay. And at the end, you say use the final weight vector times C, so currently C is 4, times the number of examples, minus this bluish area that which you summed up, which you accumulated in WA, this auxiliary variable, and that's exactly this triangle in reddish color that you need to output or need to kind of keep track of in the naive implementation. Okay, so you might have a little bit trouble understanding this, but hopefully after homework 1 and homework 3, eventually, in homework 1 you don't need to do this, but if you do, that's great. In homework 3 you have to implement this, okay? But this is very easy. It's a very, very simple trick, and this trick makes average perceptrons run exactly as fast as vanilla perceptron.